I'm Ghazarian, and today I'm going to be talking to you about the applications of calculus in medicine, more specifically tumor growth. Applications of calculus in tumor growth. Calculus is used to find the growth/decay rates, the volume of the tumor, when the tumor will become most dangerous, also known as the critical point, and when the tumor will stop growing. However, I'll be mostly speaking about the applications of calculus in calculating the tumor growth, which is the growth rate of the tumor. Tumor growth. So using the Gompertz growth model. So using the Gompertz growth model, if we are given the correct variables needed to plug into the equation, we can calculate the equilibrium growth for the tumor and the maximum growth of the tumor. So, cancer and mathematical role. So thanks to calculus and many fields in mathematics, scientists are now able to take detailed images of the tumor to calculate therapeutic doses for radiation and to even calculate the growth rate of the tumor itself. So just a little bit of background information of tumors, and here's a nice detailed image of the tumor, and you can follow along with what I'm saying. So a tumor grows based on the amount of nutrients that is supplied. So if a tumor supplies very minimal nutrients, then it won't grow that large. Tumor angiogenesis, and this is the proliferation of blood vessels that surrounds the tumor. And these blood vessels bring oxygen and nutrients to the tumor, which give it an optimal environment so that it can grow. The center of the tumor is made up of dead cells, which is also known as the necrotic center of the tumor. And tumors are spherical in shape, as you can tell by the diagram. And very obviously, we know that tumors will behave differently depending on whether they are malignant or benign. The Gompertz growth model. So in 1964, a scientist named Laird found that tumor growth could be calculated using the Gompertz growth model if you're given the correct variables to plug in, where N represents the number of tumor cells, B is a growth constant, and A is a constant for growth retardation. It is also important to note that the function will be undefined when N equals to 0, but it can be shown as a limit. So tumor growth for the Gompertz growth model. So a tumor stops growing at the equilibrium. A tumor is at its maximum size supportable with the quantity of nutrients. But how can we tell when the tumor is growing most rapidly? And it's actually a lot easier than you might think. All you have to do is you find the derivative of the function. And then you take that derivative and you make it equal to 0. So, most cancer therapy attacks the growing cells. And cancer treatments have their largest effect when the tumor is at its max growth. Equilibrium for the Gompertz growth model. So, for the equilibrium, instead of taking the derivative of the function and making it equal to 0, all we have to do is make the function equal to 0. So all we did is we took the Gompertz growth function and we made it equal to 0. And then we just isolated for N, and we found that the equilibrium of the Gompertz growth model is N equals e to the power BA. And this is also known as the carrying capacity. And if you look here, here's the equilibrium. Max growth for the Gompertz growth model. In order to find the max growth of the tumor, as I said earlier, you must first find the derivative of the function and then make that derivative equal to 0. So the function, the Gompertz growth function is over there, it's highlighted in orange. And in order to find the derivative of this Gompertz growth model, you will have to use the product rule. And so if you need a little bit of review, please refer to chapters 2 and 5 in the textbook, just so you can take a view at like some of the sample problems and see how they solve it. Down here, I just solved a few simple examples of the product rule. Here's the product rule itself, and then here are just 2 simple examples, 1 example and 2 examples. Please look at them if you need extra help. So the max growth of the Gompertz growth model. So remember what we said, we take the derivative of the function, and we make that derivative equal to 0. So first, find the derivative. Here, just the work of me finding the derivative, but the final derivative is right here. And what we would do is we would make that equal to 0, isolate for N, and we find that N is equal to e to the power B over A minus 1. Tumor growth using the Gompertz growth model. So if the growth of the tumor is able to satisfy the Gompertz growth function, we will use the function G of W is equal to W, B minus A ln W, where W here is the weight of the tumor in milligrams. Remember, milligrams, please. Remember that, milligrams, it's very important. So, for example, if you are given variables B and A are both constants matched to data, such that B is equal to 0.6 and A is equal to 0.06, we can now use this information or this data to calculate the equilibrium growth for the tumor, calculate the maximum growth rate of the tumor, and we can even sketch the function. So, first example, which is finding the equilibrium growth of the tumor. So, to find the equilibrium, we have to make the original function equal to 0 and isolate for W. And here we will see that we isolate for W and we find that W is equal to e to the power 10, which is equal to 22,026 milligrams. So the equilibrium growth or the equilibrium weight of the tumor is 22,026 milligrams. And then the example for maximum growth rate. So to find the maximum growth rate, make the derivative of the function. Derivative of the function for maximum growth rate, make the derivative of the function equal to 0. So first we find the derivative. I already found it right here. So here's the derivative. All we do is we make that equal to 0, and then we isolate for W. As I said, like the same thing with the equilibrium, isolate for W. And we find W is equal to e to the power 9, which is equal to 8,103 milligrams. We take this value for W now, and we plug that into the original function, the original Gompertz growth function. And we find that the maximum growth rate of the function, or of the tumor, is 486.185 milligrams per day. Here's just a graph that I graphed using Desmos, and it shows that the maximum growth rate here, Y value, is 486.185 milligrams per day when the weight of the tumor is 8,103 milligrams. Calculating tumor growth. So there are hundreds of types of cancer, so you can't just use one model to calculate everything. Obviously, you will be given different variables and you need more than one model. So, as I said, no one model can represent all types of tumor growth. So doctors will use different growth model equations to best fit the volume of each individual tumor. So the other ways to calculate the growth rate of the tumor. So one way, which is still using the Gompertz growth model, rather than using the original equation and finding the derivative, we now find the anti-derivative of the Gompertz growth model. So by finding the anti-derivative of the Gompertz growth model, we can figure out the number of tumor cells in the tumor. So the number of tumor cells inside the tumor, and then if we know the mass of the tumor cells, we can then multiply the number of cells by the mass of the tumor cells to find the total mass of the tumor. So here we just anti-differentiate the Gompertz growth model, and we multiply it by the mass of the tumor, and just for like an example, that the average mass of the tumor is 10 to the power negative 19 grams. 10 to the power negative 19 grams. So we take the antiderivative of it, and we just multiply it by 10 to the power negative 19. Another way to calculate it is the exponential growth model, where RT is the volume at time t, 0 is the volume at time 0, K is the exponential growth constant, and T is very obviously time. However, the thing is with the exponential growth model is that the exponential function does not take in vivo into consideration, which means that as the size of the tumor gets bigger, the growth rate decreases. Another way to calculate the growth rate of the tumor is a model based on the metabolic rate. So cancer growth can be modeled using a mathematical model based on energy conservation. So the total energy that goes into an organism's development either goes into the maintenance of its existing tissue or into the creation of new tissue. So all the energy goes into maintaining the original tissue or the existing tissue or making new tissue. So tumor growth can be represented by the equation, which is written right here, highlighted in orange, where B represents the energy the organism uses while it's at rest. The two NC and BC, these are variables that represent the amount of energy needed to maintain the existing tissue. They are the metabolic rate for an individual cell and the number of cells in a particular organism. And EC, right here, is the energy needed to create new tissue from pre-existing individual cells. And right here is a graph for the metabolic rate. And just the importance of calculus. So calculus is important for many fields of medicine, such as tumor growth, cardiac output, and blood flow. Scientists have used calculus to develop mathematical models used to simulate the growth rate of tumors, the growth of tumor volume and its response to a single dose of radiation or irradiation. This helped provide clinical insight on radiation therapy strategies and provided important information as to when the cancer treatment is most effective. Thank you for listening to my presentation, and I hope you enjoyed.